my talk is about some activities that we have done during the past years in Politecnico di Milano, and particularly at the MOX laboratory, concerning mathematics and sport, but the main area is not statistics, is not operational research, is not, let's say, data science, but is more numerical analysis and simulation. And I think even if the topics are quite different from most of the talk we have seen up to now, I think we all share a common view on the fact that sport is a very good and a challenging playground for scientific research. It is also a very good environment to do something different from research, which is innovation and technology transfer. But it's also something that helps us in communicating to broader public what mathematics can do. And what I will try to just describe is a few applications in different sports, America's Cup sailing, rowing, Olympic rowing, swimming, and a few words on volleyball and soccer. And as you will see during the next slide, mathematics in this kind of application can be used for different kind of analysis. Some are related to helping designing better tools and better devices. Some are related to analyzing and optimizing a type gesture. And some are also related to assess the rules, because as Phil very well explained this morning, having good rules is a key point to the success of a sport and keeping the interest of the public at a high level. So the description I will give is related mostly to three projects that we have carried on. One is a long-time project that we had in collaboration with the Swiss sailing team Alinghi, and I will show some results related to shape optimization of some part of the boat, free surface aerodynamics of boats, and fluid structure interaction between the air, the wind, and the sails. A second project is also quite a long-term project that we have in collaboration with another company, which is a small Italian company, but which is quite important in the rowing environment. It's called the Filippi Lido. And there I show some of the results we have obtained in terms of mathematical and numerical modeling of this kind of physics. And finally, some experience on the swimming sport related to the design of swimsuits. All these are a very large collaboration with many other people. I just mentioned here a few names that are have a big role in all these projects. So I'm just one of the people who has contributed to these different projects. And even if these are the three main subjects, I will start from a simpler case, just to try to say a few words on the fact that the same problem, even when we look at the physical modeling and we build mathematical and numerical model to solve some physical phenomena, can be built at different level of accuracy, and there's no a better and the worst model. Depends on what are the objective of a specific analysis. So if I want to predict the trajectory of a golf ball, I can be happy if my objective is of a certain type to build a very simple model, neglecting all the forces but gravity, and I'll get an algebraic relation that gives me a parabolic shape. But then I may be interested in something more. For example, I just want to take into account how the drag acts on the ball, or other Magnus effect, or other effect related to fluid dynamics. And then to compute a better approximation of the same trajectory, I will need to solve a more complex mathematical problem. It's not an algebraic relation, this will give me an ordinary differential equation. Then I may be interested in more details. So if I look at golf ball from a very close perspective, I may notice that very close to the bumps we have on the surface, which are there to reduce the drag, we can see a very, very complex physical phenomena, which is essentially related to the fact that a ball with this shape will experience less drag because will produce a turbulent boundary layer. And in this case, in order to capture this part of the physics, which is a higher order term, but it may be important in some kind of analysis, I will need to solve a much more complex problem, which is Navier-Stokes equation, for example. We will talk about it later on. But this is a partial differential equation, and will require a much more complex model to solve, and typically a much larger computational time to do it. The choice of the model obviously depends on what you are interested in. It's meaningless to do every time a solution of a simulation at this resolution if you are interested in very integral quantities, or you are not interested in very details. So and we will see that in some of the applications we will describe later on, these three levels will come back. So let's start from the first main project we were involved in since 2002. It was I'll try to give you an idea on how math, and in particular computational fluid dynamics, so the applied math that helps you in solving the equation of fluids, can help in designing a better, faster, more robust yacht. Typically, when you design a yacht, an America's Cup yacht, you will receive information from many different sources. One is towing tank, which are a large experimental setup where you can actually test a different shape of the hull and see which one behaves better. Other tests can be done in wind tunnel, where you don't have a water basin, but you have a wind tunnel, and you can test, for example, either the shape and the forces on sails, but also, we'll see it later, wind tunnel can be used also in the design of appendages, which are in the water in reality. And then you can use some simple, let's say, mathematical models, which are based on potential flow theory, which are quite fast to be solved, but have some major hypotheses that are not always acceptable, like the fact that it's describing an inviscid case. And then we have the full, let's say, simulation, which accounts for all the different physical effects, which is the one as the detailed golf ball we have seen before. So all these different sources of information are all interesting. I'm not going to say that what I'm doing, which is essentially this red block, is the most important. I'm pretty sure that without all these four other elements, the boat will be designed slower than what can be done right now with all the terms. But the fact is that you need all these because each of these contributions will help you in detailing and finding a better approximation in some specific condition. And how do you use all these sorts of information? You use them to feed what is called velocity prediction program, VPP in slang, which essentially helps you in assembling this kind of problem. So you consider, for simplicity, just a 2 degree of freedom case. So this is the boat from above. This is the sea water plane. And when this boat is moving, it will be subjected to different forces. Some are hydrodynamic forces acting in this direction in this case. Some are aerodynamic forces acting on the sails. When the boat is moving in a steady way, these forces are in equilibrium, and which means that somehow you can reach this equilibrium solving the Newton's law. So mass times acceleration is equal to the sum of the forces in the different direction, and obviously the same holds for rotational equilibrium. And how do we use those sources of information? Just to feed this model and computing and, let's say, estimating the forces acting in the different directions. Sometimes the forces are better estimated by calculation, sometimes by measurements, sometimes by wind tunnel experiments. And when you solve these, typically you can find an equilibrium condition where the the resulting force are going to be 0 and there's no acceleration anymore. And this will give you somehow an indicator of the goodness of the quality of your design, because a faster boat with a reasonable attitude will be the better choice when you compare different solutions. So the idea is that you need to build up tools that helps you in having this estimate, the estimate of this quantity in a different speed, at a different attitude, as accurately as possible. And the big problem of experimental setup in towing tank or in wind tunnel is that they are extremely expensive. Anytime you have to set up a wind tunnel test or a towing tank, you need to build a model. This model can be very, very expensive, and it's very difficult to test more than a few different designs. So you should go, I mean, it's important to go in the wind tunnel and in the towing tank, but you should go at the end of your design process, where you have to choose between a few different solutions. Most of the work should be done before using CFD, which stands for computational fluid dynamics, where you can explore a much broader parametric space. And here, just to get into some detail, but just to identify which are the most critical things in this kind of physics. These are the appendages, are the part of the boat. These are old style America's Cup boat. The 35 edition just ended a couple of days ago with these new multi-hull boats. These results are on whole style monohull, but which are completely different topics. I mean, designing today an America's Cup boat is more related to designing a plane than a boat, because it's most of the time out of the water. But we will come to that later if you're interested. But the main things that you should be able to do in a reasonable way and in an accurate way to help the designer in getting the best solution is being able to simulate very, very complex flow regime, which are the one where you have both some region where the flow is laminar and some region where it's turbulent. You have to be able to predict the deformation of the sea level when the boat is moving, and you have to be able to predict the shape of the sails, which is not the design shape, but it's the shape that the sail has when it's acting, when the wind is acting on it. And I mean, these are just keywords to tell you what is the approach that we used, but I won't get into these details. I just show one slide with a few, let's say a few slides with a few equations, but without detailing the content, the mathematical content. I'm just interested here in showing that the kind of problem we need to solve to address that physical complexity is unfortunately the full model. So we need to solve the Navier-Stokes equation, which are the equations governing the dynamics of any fluids, water or air. And in this case, we need to simulate a two-phase flow. So this equation holds with I ranging between 1 and 2. 1 is air, 2 is water, and you have a similar set of equations both in air and water. But then the two domains are somehow interacting, so you need to set up some interface condition, which is of this kind, which means that you need to guarantee that at the interface gamma velocity is continuous, and let's say the normal stress tensor is continuous. These are, for who is not familiar with this kind of model, are essentially second Newton's law for continuous mechanics, because this object here is essentially an acceleration. This one is describing all the stress acting on a particular element of water, and this is continuous. And in addition to this, let's say, second Newton's equation, you have a constraint prescribing the fact that the velocity field should be divergence free. And okay, these can be formulated luckily in a single model where you just have the density and the viscosity which change sharply between one fluid and the other. Okay, just why I'm interested in showing also this level of the equation, because then what I'm want to stress is the fact that to solve this problem is in such a complex domain. I mean, this is just a 2D sketch, but you can imagine the geometrical complexity of the shape of a boat. You need, I mean, there's no way to solve this equation in an analytical way. I mean, nobody will never be able to solve this equation in this domain with an analytical formula. So we need numerical analysis techniques to approximate this equation and to somehow subdivide all our domain in very, very small elements and impose the governing equation, which are related to conservation of mass and conservation of momentum on each of these elementary elements. The problem is that these elements, these small pieces in which the full domain has been divided in, are many. I mean, you have to describe very, very small detail to be able to capture the physics you want. And these results typically in very, very large systems, which are at the end linear systems, may be solved many times because you need to face the nonlinearity, but at the end the cost, the large computational cost is related to the fact that the system you have to solve is of the size 200 million times 200 million. So you need very efficient numerical techniques to solve linear system, and this can be done nowadays on large HPC systems. And these typically, I mean, the main, here we are not doing things for solving an academic problem. We need to respect the timing of the design team. So this problem can be as large as we want, but this should be able to be solved in let's say, few hours, not in months. Otherwise, it's useless. It's a useless tool. Why this is important with respect to what we can do in wind tunnel or tow wind tank? Because you can really explore a huge range of design options. So no one ever built a model of appendages with this shape of winglets or this shape of winglets or a set of 4 wings. Why? Because it's very unlikely to be the optimal solution, and it's not worth it to build a model to find something which has a very, very small probability to give a substantial answer. But the advantage of numerical simulation is that you can explore a wider parameter space, and sometimes you actually find that something that by intuition doesn't look to have much possibility to be successful can actually be interesting. And the other point is that whenever you do an experiment in wind tunnel or in tow wind tank, you need to know a priori what is your interest. So you need to put balances or pressure probes or whatever you want to measure. You need to know that before doing the experiment or the run. In this case, what you get when you run a simulation is a full solution, velocity, pressure, and any turbulence quantity in any point of your domain, and you can post-process these results and identify very, very peculiar structure of your flow, which you will never see in the wind tunnel unless you already know that there is probably a structure over there and you put some sensor over there. Just to, as a matter of example, one of the big player in the design of appendages in America's Cup are the winglets. So these small wings that you put on the bulb, and the position and the shape is something that is not known. I mean, the optimal position and shape. And if you compare the last monohull America's Cup, you could find someone having winglets in front, on the back, in the middle, sometimes 4. The idea is the same as the winglets on the plane. You all have seen this object at the tip of a plane. Why this object is there? Because they found out a few at the beginning of last century that the effective the efficiency, let's say, of a wing, of a finite wing, so not a wing with an infinite span, which is not realizable. A finite wing will always have an additional component of the drag, which is related to this object lambda effective, which can be smaller or greater depending on how long is the wing. The problem is that you cannot build a very, very long wing because you have constraint, structural or logistical constraint in the airport. So one way to increase this quantity and in this way to decrease the induced drag is to build these winglets. And a few years ago they found out that the same applies also to boats, and somehow the keel of the boat acts as a wing. Okay, why should act as a wing? Because you have a sail over there, the wind is pushing, and if you don't have something that push on the other side, your boat will move alongside with the wind. Okay, so you need something that create a pressure differential between the leeward side and the windward side. A counter effect of this is the generation of a recirculation. Here you have high pressure, you have low pressure, so the flow will recirculate, and this recirculation can be reduced by putting some winglets, and you will see the effect. So this is the recirculation measured in terms of vorticity. You have a very large red spot in the middle here, which indicates large vorticity, and if you put the winglets, okay, it's quite dark, but you can see that there are winglets here. This vorticity is much more spread, and the peak is lower. And we have found during this analysis that there is an optimal position which maximizes this reduction. All this obviously is nice. You have pretty picture, you have numbers, but then the sailors and the designer will not believe in you unless you do some cross-verification with experiments. And here there is an interesting story, because this is probably one of the few times in the history of this wind tunnel, for sure of the history of this wind tunnel, but probably of most of the wind tunnel around the world, that the actual model that we put over there is larger than the real object. Because whenever you want to simulate something in a wind tunnel, you can do a model, you can change the size, but in order to get some reasonable results from this experiment, you should be able to create this an equivalent Reynolds number. So the Reynolds number of a flow problem is related to the density of the fluid, the velocity, the length, and divided by the viscosity. So the problem is that whenever you are testing a plane which is much larger than the wind tunnel, in a wind tunnel you can build a smaller model, and it's enough to make the flow moving faster than the plane itself. In this way, if flow is smaller and u is higher, you can have the same quantity, the same Reynolds number. The very big problem when you are testing in wind tunnel with air, something that lives and works in water, is that you have also a density which is times 1,000 times greater in water than in so let's say rho over mu is almost 100 times greater in water than in air. So to respect this analogy, you need sometimes to build bigger object in order to be able to respect the analogy. So why we did this? Just to compare the experiments. In particular, this is a test on where the transition between laminar and turbulent flow occurs, and we could recover some good correlation between, let's say, experimental measurements and the numerical results. These are just images to show that this kind of solution show you the wave pattern, so the solution of a free surface problem where the actual sea level is moving depending because of the motion of the boat. And the same kind of tools have been used both in old style monohull boat and this was the first edition of the America's Cup where multi-al were in, and actually Alinghi participated to that edition, not to the last couple. Just a few words more on this kind of application. I didn't mention the fact that here everything is fixed, so we assume that our numerical model is a geometry which is fixed in the water, and we look at the air and the water that moves around something which has a prescribed position and attitude. But we can also, let's say, describe and predict the motion of the boat, and in particular you have to couple the dynamics with, let's say, the fluid dynamics with a simple, just rigid body motion of the boat. And in particular, one thing that you can do is writing your equation in terms of two reference systems. One is a global reference system, the inertial one, and the second one, which is attached to the boat. And thanks to the definition of some rotation metrics and the boat tensor of inertia, you can actually write the standard equilibrium, linear equilibrium, and the angular equilibrium, where omega dot is just the angular acceleration, has to be, let's say, transformed by this rotation and rotation metrics. But at the end, it's a 6-degree of freedom system that you can solve with your favorite ODE solver. And okay, here I have to move things on this PC, so just to give you an idea of this. Oops, okay, doesn't work. No problem. There was a nice animation, and you can imagine. Here you would have seen, if the movie was working, that this boat would have moved under the effect of this wavy frame. This is interesting because you can also assess and study the effect of the dynamics on the boat in terms of resonance. For example, you can do what is called seakeeping analysis, and all the boat has a proper frequency, okay? And if you put a boat with a wrong proper frequency, where that frequency is one of the main component of your sea wave spectrum, you have the risk of going in resonance and having very, very large motion of your boat. The same things of validation applies to the analysis that you can do on the free surface, and in this case the wind tunnel is not wind, but is a water tunnel, which is called the wind tunnel. And this is just to say we have done some cross-validation with experiments, so we can trust our numerical results. But once we can trust on one design, we are free to run many more numerical simulations without doing the same in the experiment. This allows to reduce enormously the cost. Having said that, the cost of the design of an America's Cup is huge. It's of the order of 100 or 200 millions per boat. So, and this is just building one boat and doing a few experiments in the winter. Another aspect related to boat design is a very complex problem, which is the prediction of the shape of the sails under the effect of the wind. This can be quite easily done when we look at upwind sailing. Why? Because when you are sailing upwind, your sails are actually acting as a plane wing, and the flow is attached. So you don't have large separation, and you can use simplified flow models, which are very, very accurate in this case, in this regime. Whenever you have to simulate or you have to analyze a downwind case where you have a spinnaker or gennaker, here this sail is actually acting as a parachute, and you can imagine that the flow around this object is a much more complex phenomena. It's not attached, and in order to be able to simulate this, you need the same kind of numerical tools for fluid dynamics that we have seen before, but you have to, obviously, to take into account the fact that here you don't have a rigid body which just maybe moves, but moves rigidly. Here, this is a very, very soft tissue, and the way, the shape it takes highly depend on the interaction between the structural movement of this tissue and the flow motion. And this is a problem which requires a very involved model where just in terms of a simplified notation, you have to imagine that if you have a solver which is able to give you, given a pressure distribution on the sail, is able to tell you how the shape of the sail will be under this pressure. And then you have another solver. The first solver was called struct, is a structural solver. Then you have another solver which, given a certain shape of your sail, will tell you, okay, the flow around that shape will be this one, and in particular, the pressure will be this one. Then, obviously, this is a problem, this is another problem, but the two are coupled and are very, very strongly coupled, and in order to find the equilibrium solution, you need to iterate many, many times in order to reach the solution at convergence where the structural position is conforming with the pressure that you obtain. And we have done it not again on an academic exercise, but defining a design tool for Alinghi, coupling some commercial and some in-house code, and realizing also a tool that should be used not by mathematician or numerical analyst or a scientific computer guy, by designer and sometimes by sailor themselves. So they were able to control all the background simulation without knowing any details on the numerical model. And this is an example of result. If you don't tune, I mean, this is why this is useful, because you can exercise your trimming of the sails without, or in a, let's say, in a more controlled framework, and you can help both the designer and the sailor to analyze what happens when you don't trim correctly a sail. And for example, here, if this Genoa is not trimming correctly, you see you have a large separation here, which typically gives you a very large force. If you trim better the sail, you can have a much more efficient solution. Okay, these two solutions are obtained by changing one number in the simulation, which is the length of the sheet attached to the corner of the Genoa. All the rest is a result of the simulation. Okay, I skip this because it's not that relevant. So there are some tools that helps us in automatically choosing the optimal shape, and in order to do that, you have to couple different software, different library, different models. I'm moving to a second application, which, this is the end of the first application. The results. The results were very successful in 2003. We won the cup, and we bring the America's Cup in Europe for the first time in the America's Cup history. And then we defended the cup, the edition 2007, and unfortunately we lost with the multi-hulls, and we stopped to work on, actually Alinghi stopped to work on the America's Cup after that. A second application, which is somehow related, but is a very, very peculiar characteristic, is, so you have a boat. This is a much simpler boat model, because the shape is much more slender, the fluid dynamics is much more easy to solve. The small problem here is that you have a boat that is a few kilos, like less than 100 kilos, a few tenths of kilos, and you have 8 guys, 90 kilos, moving on board. So the dynamics of this boat, the behavior of this boat is incredibly affected by the fact that you have this very, very big movement of 95% of the mass, of the total mass of the system moving on board. And also you have unsteady forcing turn coming from the oars and so on and so forth. So what we did for this project was to model, completely reconstruct the system of the full boat, oars and rower, then building some, again, fluid structure system to couple the movement of the boat with the fluid dynamics, and then analyzing and designing writing a design tool for them. The system is exactly the same as before, so you have equilibrium of linear equilibrium, so acceleration of the center of gravity times mass. These are the forcing. The forcing term are the gravity plus some hydrodynamic force in the water. And then you have the same where here you have the forcing, the momentum acting on the angular degree of freedom. But then you have all the inertial term coming from the body moving on board. So all these terms, which were the one complex to be introduced, are related to all the different forces related to the fact that you have the motion and the oars moving in the water. And so in order to compute all this quantity that close the system, we needed to write a second system, which is the equilibrium for the body. So we had some measurements, kinematic reconstruction, which help us to solve an inverse problem and compute the force acting on the different components of the human on board. Obviously, the force that the human is acting on the boat is the same with different opposite sign as the one that the boat is acting on the human. So most of these forces are the same with opposite sign that the one up here. And just to make a short history, putting together this system with the previous one, you can actually assemble a system. This is just a 6-degree, a system of ordinary differential equation of dimension 6, but you have full of parameter to fill. And to really close the system, you need two additional elements. One is a model for the oar, so how efficient and what is the description of the force during a stroke phase. And this is a very simple model. There are very much more complex models in the literature, but the model was already complex enough. And then you have something that estimates the hydrodynamic force. And here, since the boat is much simpler, even a very reduced model based on potential flow theory can be enough to solve things. And this means that that system, the simulation of the dynamics of the boat, can be solved in a few seconds, almost in real time, at the same time as the race occurs. Obviously, you can also try to look at more complex fluid dynamics using the same tools that we have seen before. There is a small issue here that as long as you do a model which is just 3 degrees of freedom, so you look at your boat on the symmetry plane, let's say, and you just have, let's say, a yaw motion, a surge motion, and I mean, you can move just forward in vertical direction and just in the one angular direction. This is easy and everything works. If you want to take into account all the 6 degrees of freedom, you face a big difficulty, which is the same difficulty that anyone that has got once on board of a Olympic rowing boat feels. So it's very, very difficult to stay on board because the system is physically unstable. So the rowers are very good in keeping the equilibrium and controlling the equilibrium. So what we needed to insert in our model in order to do 6DOF simulation is something, some control model that was able to mimic the controlling action that the rowers were doing. Again, this is a very, very simple linear control model, but with this control model we could actually solve a full solution for the 6 degrees of freedom. This is what happens if you run a 6 degrees of freedom without control. You just have something that, okay, this is not physical in the sense that you will lose your control much before, but because this is somehow a numerical instability which is actually related to a physical instability. If you add the control model, you can actually predict a stable solution. Obviously, you don't see here anything because the scale is the one of the uncontrolled system, so I show you the stable solution from a better point of view. So these are the evolution of the 6 degree of freedom, surge, sway, heave, and the triangles in the, let's say, first 20 seconds of a race. And why this is useful? Because you can actually compare both the design of boats, because if you change the design of boat, you may have changed a little bit the position of the rowers on board, you may change the shape of the boat, we change the fluid dynamic force. So it's a tool that can be used by both boat designer and by also by athletes themselves or trainers, because for example the same boat can be more efficient if you put, these are the number that characterize the 4 rowers on this boat. These 4 rowers are different weights, so the first one is heavier but is also stronger, okay, so can give you more power, but is heavier, so somehow this additional weight penalize the boat. And you can analyze with a tool like this which is the better position of this rower, if it's better to put it on the front, on the first place, on the second, on the third, and so on. Not only that, you can, and we have done it in collaboration with the Italian Federation, you can actually construct ad hoc model for the power that each athlete is putting on the oar, measuring the athlete-specific quantity. So you can replace this simplified shape with something which is related to the athlete himself, and also you can test how good is the athlete in reproducing in a very accurate way always the same movement. So this is just to say that it's not just the peak of force that counts in this model, but also the ability in reproducing in a very constant way the same movement. Again, related on rowing, we have done another project which is somehow related to the previous one, because we use in the same tools, but it is for a different problem holder, which is in this case the International Federation of Rowing, who had a couple of years ago had to take a decision related to rules, and here I come back to the discussion about the importance of rules. So there is a prescription still today that you cannot run an Olympic rowing race in a basin which is shallower than 3.5 meters. So this is a lower limit. Your basin should be at least 3.5 meters deep. And obviously this is a big issue, because if you are a city that is interested in organizing an Olympic game in a few years, and you don't have already this kind of facility, it's much cheaper to dig a 2-meter basin than a 3.5 meter, because it's almost the double of material that you have to put somewhere. So they have been asked by a few candidates to assess the fact that this restriction, the current restriction, is reasonable or not. And we help them in analyzing how this quantity, so just the depth of a basin, is influences both the performance of the boat, but also the fairness. So there are in Olympic rowing, you don't have a world record. I mean, the basins are so different that there's no a time which is considered a world record. what is important is that the race should be fair. So all the lanes should guarantee the same condition to everybody. And what we have done is using the tools that we have seen before, but also other tools that are able to compute the recirculation of the flow inside the basin, which is typically induced by the wind, and analyze whether reducing this limitation, I mean, this minimum deep depth limitation could affect somehow both performance and fairness. And what we actually found out is something that would be, it's quite a standard result in shallow water modeling. There is a big problem when your boat is moving across a region which is called critical regime, which essentially is when this is a quantity, is a non-dimensional quantity, which is the depth number, defined as the velocity of your boat divided by the square root of the gravity g times the depth. If this quantity is around 1, you are in the critical regime. And actually, when you are in the critical regime, your pressure drag, so the resistance, one component of the resistance, has a very large increase. And it's not a good choice to work in this region, because just going a little bit slower, you will get much less resistance. Just moving a little bit faster, you will have much less resistance, and this is just the place where you have a peak in performance. And we have done this analysis on the specific rowing boats, because this is, let's say, a known result in boat design literature, let's say. And what we have found actually is that the current limitation, which is 3.5, has a critical velocity of 5.86, which is exactly in the range where rowing boat acts. So we are working most of the time, because obviously this is the 3.5 is a lower limit, but this is most of the time the quantity, the depth that the new basin has, because nobody is interested in doing something deeper. And this is probably not an optimal choice, because, for example, the double, so the two rower boats, are exactly working across this critical regime, and in fact you see this peak. So the suggestion was to consider the possibility to change this rule. Obviously, there are other factors that should still be assessed, and indeed the rule change has not been designed yet, which is related to the, let's say, biological equilibrium of this kind of basin, which can be more difficult to maintain if the quantity of water is less. So there are still, this is still an open issue in terms of the rule decision. Last things, and then hope, yeah, I have 5 minutes more, is an application on another sport. I wanted to mention also this one. This has been carried out in 2 different moments at MOX. First one where I was not there. There was some colleagues that worked on this first problem. I was involved in the second one. Obviously, these are all projects that comes a few months before the Olympics game, because they want to sell the new swimsuit in a very visible event. And typically the time is very short, and so on and so forth. And what we looked at in this second project was an assessment of one of the changes that they have done on these, I don't remember the name, new Air Revolution swimsuit of Arena. And the big change was that all the sea wings were removed from the surface of the swimsuit. So you had a very, very flat and smooth surface everywhere. So removing all the sewing that were in the different position on the previous model, they claim to have some advantage in terms of reducing the resistance. And what is difficult in this case is that you have a problem, which is a fluid dynamic problem very similar to what we have seen before. Again, is water moving on a surface. The problem is that here the typical length scale are very different, because you have a very, very small scales close to the, you are interested in simulating what happened just across the single wire of sewing, but then you have to consider that these sewing are around the body which has a certain shape and which has a length scale of few order of magnitude more. So we have set it up a multi-scale model to deal with it, and we end up with some estimate of this advantage. Obviously, the advantage is there. Whether or not such a small change in resistance, so these are the reduction of resistance in terms of newtons, and this is in percentage for the different sewing in a different position of the swing suite, and this is a total quantification. So at different speed, the advantage was below 1%, but still it's not a negligible quantity. What we have done is also trying to extrapolate from this drag reduction what may be reduction in lap, let's say, a gain on time for the race, and this was done based on a very, very simple model where we just accounted for the change in resistance on the, this is again second Newton's law with propulsion, a very simple model for the propulsion, and a model for the resistance where the change in the drag is considered. And here we could see that the amount of second that you, of millisecond that you save due to this change in the design can be not negligible. So can be the difference between a world record or not. Unfortunately, after this edition, all the rules in by the, unfortunately or not, I don't know, because maybe it was a good choice to remove the possibility to do whatever they want on swing suite, because in these Olympics game, many world records were broken. Most of them related to, we hope, technology and not other issues. But anyway, this kind of analysis was stopped after that edition of the Cup. We have, oh, sorry, of the Olympics. We have done some work also on motion of the stroke, but this is, I can skip. I want to discuss in a couple of minutes these two last slides. So what is interesting in, for me, what I like in the job we do in our lab. In our lab, we do math applied to sport application, as in this case, but applied to many other industrial or biological or medical problems. And the interesting part is that we can learn from one application and transfer what we learn from one application to the other. For example, what we have learned during a few years of work on fluid structure interaction in the simulation of the cardiovascular system, so blood flow interacting with the arteries, we have used in the design of fluid structure interaction model for sales. But then what we have learned here, which is a very different structural physics than what you have in arteries, we have applied this to completely different subject, which is how a package of Tetra Pak is deforming when it's filled up. Okay, and this the same apply to many different subjects which enter in this kind of modeling. So turbulence appear here, appear in the heat and the ventilation of a room, appear the free surface in sport application or in bioreactor problems. Heat transfer appear again in many different problems. So what I think is the message is that, and this was what was something that I was mentioning at the beginning, is that sport is a very nice place to work because it offers complex problem to be faced, and then what you learn there you can apply in different application. And then just to mention the fact that even if these applications seems a little bit far from what most of us we have seen in these couple of days, we are moving to a situation where I believe the physical models will get more and more in interaction with the statistical model, the research operation model, the game theory model, and some good examples are already in place. For example, in the collaboration we have with our spin-off Moxoff, and now with this new company that just the recent company MathSport. If you were here yesterday, Maria talked about this subject. We have started working with them a few years ago on the modeling for volley, but now this is something that is completely developed by MathSport, and they are merging the physical modeling of how the ball reacts and behaves with the statistical model that helps in predicting the success or the analysis of the gesture depending on parameters. Another example that on which we have worked a very little bit, but I think will be an extremely interesting field for Matematica and sport is related to network analysis. I know that there are many applications already around on this subject. I didn't see anyone in these couple of days, but I was not here on Monday, so maybe I missed one. But I think this is something that will be very interesting in the coming years. So applying all the network analysis tools that are nowadays very well developed and are developing faster and faster due to many other applications such as social network, for example, applying it to analyze the interaction between athletes, and we applied it in a very simple model on on soccer games. Okay, that's all. This is just a few references if you're interested, and thank you for your